so this is something I do want to kind of address here. If we take a look at what I've got drawn up on the board, just for that first step, so I guess I'll draw it so we can see it at home too. I have the electrons, and I'm not going to draw the other piece, coming out to attack that hydrogen, but my source of electrons is coming from the pi bond. So the result that I would draw would be this guy. Does everybody see that? And then I'd have a formal positive there. Everybody okay with that? Okay. Which method is better? Book or me? Actually, let's finish out. What does the book's result show? We didn't touch the pi bond, right? Everybody see that? So who's right? Book or me? Why are you saying they both end in the same spot? The relationship between those structures is that they are resonance. Okay? So mechanistically, we're doing the identical thing. Okay? There really isn't a huge difference there. However, I'm wrong. Why am I wrong? And even though I'm wrong, I will always draw it this way.
Because in the top structure, all the atoms have their octet filled.
So the top structure is more correct because if we look at the product shown from those arrows, we show satisfied octets. So given the choice of those two resonance structures, when I'm trying to draw them out, I want to draw whatever is going to get me to the best resonance structure. Because I have the satisfied octets, that's the best one.
Best resonance structure can't react. So.
If I want to know something about doing a mechanism, I want to know how the structure is going to react. What is it going to do? Where are the sites of reactivity? So if I'm trying to figure out a mechanism, I'm going to focus on not the best Lewis structure, okay, but the least worst Lewis structure, or the first not best, the second best resonance, okay, because the second best resonance now draws attention to the fact that it's not the oxygen being positive, it's reactive, it's actually the carbon. I now have an electrophilic site. So I will focus on trying to get the chemistry to occur through so that I know what to do with this. Okay? As long as I can acknowledge that my structure is indeed invalid, according to best practices for Lewis structure, I'm okay with that. And as long as you can recognize that, I'm also okay with that. Okay? So I want to make sure you can see it. Why else might I draw what I drew? Why else would I use my method? Because we just addressed saying the product I drew was crap, but that product allows me to see chemistry better. Okay? So there's kind of an advantage to that. Why else would I preference my reaction over the way the textbook is showing it? It's the same number of steps, actually. Yep. Even if we move to the next part, you may say, well, you can see the positive for nucleophilic attack. The nucleophile could just as easily attack the neutral carbon as it could attack the positive carbon. You're just adding a secondary arrow, which arguably needed to be there anyway to show the resonance. So there isn't a step reduction.
The pi bond is more reactive.
Okay? This goes back to arguments that we've had about the reactivity. Okay? When we're going to run a reaction, what electrons are we going to use? The most reactive, the highest energy electrons. Those are the ones that we should keep our focus on because those are going to be the ones most likely to react. If we look at the electrons that the textbook used, they're using the lone pairs. The lone pairs are located in what orbital?
P.
There's a hint.
Oh.
They're located in an sp2 orbital. Where are the electrons that I use to react?
P orbital.
In a p orbital, or coming from our pi bond, the p orbital is higher in energy than our sp2 because the p orbitals are further away. There's more p character. So I would make the argument that the p orbitals are more active. That's why I would draw my mechanism starting there, because those are my highest energy electrons. Okay? Again, it results based off of that pure arrow pushing an invalid structure. So it's bad mojo to draw that. Okay? But by reinforcing that within my own head, it can help me remember the reactivity and keep that focus on the reactivity of the electrons. Does that make sense? Okay. So for those at home, because I'm not going to show out the whole mechanism, I think we settled on 6 steps. Because we got them on the screen here, or on the whiteboard. Our first step was what kind of a reaction? Acid-base. Step 2. It's a nucleophilic addition. Step 3. Acid-base. Step 4. 2, 3. So acid-base, nucleophilic addition, acid-base. Oh, that is acid-base. Sorry. Step 5. Nucleophile elimination. I'm now showing resonance. Should you show resonance? There's all sorts of arguments back and forth on that. Resonance allows you to say that that reaction occurred because you're showing a stable intermediate. So it's not really a step 6, but I'll just write resonance in there. Step 6 is the final acid-base step. So if we go through and look at it, in the 6 steps where we did reactions, acid-base, 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 acid-base. 4 of those were acid-base reactions. Okay? Virtually everything we're doing is some form of an acid-base reaction, and we have to time the placement of those correctly. If we do them in the wrong order, we can end up generating bad leaving groups, that strong base in that acidic environment. Okay, so we have to be careful with that. Make sense? Okay. So, here's a fun one. What happened in this reaction? What happened? There's a somewhat hint. They are color coding this. Oh, that makes it so clear. Thanks, Mike. That red oxygen has somehow inserted itself between the carbonyl and that ring. Yeah, it's totally obvious, right? When we did it with the Grignard reagent, we did single electron transfers. It made sense. Okay? We could see those electron transfers. And yes, it was kind of confusing, but at least we could stack that out. This one I find much less obvious. Okay? Add to the fact that what is kind of bizarre about the structure we've got shown in red? What is special about it? Hint, it's in the name. The acid isn't quite the important part, but you're right. It's a peroxy. CO3H. COOOH. Okay. Where have we seen those show up before? Also as a hint, it's in the name. MCPBA. Where have you seen MCPBA?
Electrophilic oxygen.
It generated an electrophilic oxygen. Okay. Electrophilic oxygen that was also a nucleophile because MCPBA was used to convert alkenes into epoxides, that three-membered cyclic structure with the oxygen in it. Okay? So that's kind of bizarre because our happenstance, our conditioning for MCPBA is that oxygen should act as an electrophile because it's reacting with an alkene as a nucleophile. And yet, when we take a look at diphenyl, let's just say benzophenone, okay, how does benzophenone react?
An electrophile.
That is very cleanly an electrophile. You should see no other chemistry within that structure. That is a carbonyl carbon and nothing else. We're looking very cleanly at a partial positive. We got nothing else left with it. Okay? So if that's acting as a positive, what does that mean the oxygen has to be acting as? It has to be acting as a negative. Okay? Which is weird out of the gate because where we saw this before was the oxygen acting as an electrophile. Technically, remember, it was acting as an electrophile and a nucleophile simultaneously. It was both pieces. Okay. So somehow or another, that negative is going to have to interact with this, which is going to create one nasty, messed up looking structure that somehow falls apart into the phenylbenzoate. Okay. If we clear a lot of this away, then talking about this thing called migratory aptitude. What is migratory referencing? Birds are migratory. What are they doing? They move. Okay? We're talking about the ability for something to move. Okay? Let's just say for the giggles, the oxygen somehow gets inserted in there. What is moving? Could try electrons, but if we take a look at our migratory aptitude, does it say anything about electrons moving? No. Okay. Technically, electrons have to move, but they aren't listing it as electrons. They're listing it as groups. What is moving if we insert that oxygen there? Does it make sense for me to insert that oxygen as shown? Are you guys okay with that attack? Why are you okay with it? It's attacking the carbonyl carbon, which is partially positive. Yes, we've got some charge structures floating around, so we can neutralize those. Make this just an OH, just to make that happy. Okay. To go from that intermediate to our phenylbenzoate, what happened? The phenyl left and then came back. You mean the electrons that were between those carbons left with the carbon and then came back to the oxygen. What happened in blue up above? Okay, so we're hearing a new word, so let's hold on to that new word. And because you used that description before, see if you can use your same description. The phenyl left, right, and then came back. Describe what happened in blue in the upper right. What did that purple group do? Just call it P.
Broke off from that bond and then attached to the positive.
Okay. If we go through and look, it broke at position 1, came back at position 2, right? Broke at 1, came back at 2. What happened in the weird-looking Baeyer-Villiger system? It broke at position 1 and it came back at position 2. What word did you use to describe the blue reaction in the upper right?
Rearrangement.
Yeah, it's a rearrangement. What kind of rearrangement is that? It's a methyl shift. Technically a 1,2 methyl shift because we took a methyl group from position 1, put it at position 2. Right? What did we do in this Baeyer-Villiger reaction? We did a 1,2. What did we shift? A phenyl. We did a 1,2 phenyl shift, also known as a rearrangement. What are they calling it? Migratory aptitude. Why? Because shit's confusing. Okay. So what's happening is we do get a nucleophilic addition and then some weird stuff came out of it. Why would we get weird stuff coming out of that? We didn't get weird shifts like this before. What about this intermediate is causing that weird shift? Ever so subtle with the hints. If we do that shift, I can kick out a carboxylate, a conjugate base that's relatively weak and stable. That can be ejected from the structure. I'm looking at a nucleophilic elimination or nucleophile elimination. Okay? So it's ugly and kind of pretty at the same time because you're doing kind of a neat thing here. You're starting with a ketone and you're ending with the ester. Okay? In this case, do we care which of those two groups? Let's call it blue A or blue B migrates. Why not? They're the same thing, so we don't care. Right? But what happens if this is now this system? Are they now the same thing? Blue A and blue B the same thing? No, one's a methyl group and one's a phenyl group. Well, would it change the product that we got out of this? Probably. Okay. So let's clean up some of this. What would happen if A was the one that migrated? Okay. So our electrons come back down to reform the pi bond, and then A migrates position 1 to position 2. What would our structure look like? Oh yes, exactly. It's totally easy to describe, Mike. Thank you for asking that question in such an easy and clear fashion. Why, you're welcome. B, what would B look like? Let's try it this way. Is B the same thing? Ooh, frantically shaking of head, no. What would happen in B? The electrons come back down and now the phenyl shifts. The result is yeah, two different products. Two different products, what does that mean? Number one, that would be a crap yield. Or two, there's something selective about it. There's a reason why one would shift over the other. You mean like a migratory aptitude? Yep. That is exactly the case. What is happening in our migratory aptitude? Hydrogen, very likely to migrate. An aryl group is next most likely to migrate. What is an aryl group? An aromatic structure, which we officially haven't talked about. A benzene is an aryl group. So aryl groups are more likely to migrate than hydrogens. Tertiary, more likely to migrate than secondary, more likely to migrate than primary, more likely to migrate than methyl. Which is our product, A or B? B. The phenyl is the one that migrates. Right? A does not happen. How do we know A does not happen? Because of the migratory aptitude. Where did we get the migratory aptitude from? Why not both? I have no idea. I've gone through and tried to explain what's going on with that, and I can't find a nice clean pattern behind it. Okay? Tertiary over secondary, maybe it's the stability of carbocations. hydrogen can stabilize positive charge better than carbon-ish, or at least it's more common, but that doesn't explain the aryl group. We shouldn't get a positive aryl group. Taking a step further, it's an aromatic, it's rearranging with electrons.
Aren't aryl groups still more stable than all the rest of those?
Not as a carbocation. That's why they didn't react in SN1 conditions. Right?
But it's not.
And it's not shifting as a carbocation, it should shift as a carbanion. In which case, which should be more stable? A hydrogen or a methyl group?
But after it shifts, like is the final product, wouldn't that be more stable with an aryl group than a tertiary alkyl group? But if you just look at the products each day, wouldn't that be more stable to shift?
How does that stabilize? What are you stabilizing in that product? Take a look at A and B. What are you saying is more stable in B than A? If you can explain that to me, that would be awesome, because I would like to hear this. If we look at A versus B.
I mean, could it be resonance from that oxygen right there that's attached to B?
So you could say that the oxygen does resonance with the phenyl group. What if it was hydrogen?
Yeah. Well, hydrogen would just neutralize some of the charge.
What charge? There's no charge there.
Well, any electrons, I guess, not charge, but it would neutralize electrons.
But what electrons? You're under acidic conditions. There's nothing to neutralize. Yeah. At the end of the day, what I ended up deciding, which is a bit unfortunate, it's such a narrow niche reaction, you should just memorize the migratory aptitude. Okay. You aren't responsible per se for that mechanism. We just walked through the basics of it on how that had to happen. Right? And yes, that's not an easy one to just look at and say, okay, this is what happened. Within the context of what we've looked at, that's how we would try and apply and match that up to force it to happen. Okay? So hydrogen, then aryl group, and then tertiary down. That's the best I got for you, unfortunately. I apologize. Not unfortunately, I apologize, but I apologize, unfortunately.
For this, is the reagent that we should memorize is just MCBA, or is there more?
You shouldn't be memorizing MCPBA. MCPBA is an example. What was the part of MCPBA that reacted?
Nucleophilic oxygen.
The nucleophilic oxygen out here. Okay? So if I gave you just an alcohol, would we expect this to happen? It has a nucleophilic oxygen, so why does that not happen? It's not just the nucleophilic oxygen. What else needs to be there? Yeah, I think I'll accept that. We need a good leaving group attached to that nucleophilic oxygen. So we need our nuke ox, and we need a leaving group there. There's very few reagents that satisfy that. Okay. The full-blown mechanism, do you guys actually want to see it? I'm going to take that as a yes. We'll just walk through it really fast. Okay. You start with your ketone. Notice that the very first step is an acid-base reaction. We didn't actually talk about the acid-base reaction. We should be thinking about it from the previous state because of this little guy down here. Okay. We talked about that. That's our triflyl sulfuric acid. Okay. That is a strong acid. It's strong enough to protonate the ketone, which is really what's starting the cascade. That oxygen from our MCPBA is a nucleophile, but remember, it's that nucleophile electrophile thing. So it's doing both. It's not a super good electrophile or super good nucleophile. So to force it to act as a nucleophile, we need to make sure the electrophile is as electrophilic as possible. That's why we run under acidic conditions. Right? We then get the nucleophilic addition. Right? We'll get the neutralization of charges. Right? And then all hell breaks loose with just a nucleophile elimination, which is really the elimination causing a rearrangement and a loss of the leaving group. So it's a giant cluster bomb that net result is just a nucleophile elimination. Okay? But it is a pretty complex nucleophile elimination. At that point, you just do another proton transfer, to end up with your final reaction. Okay? Remember the migratory aptitude. There's few things I tell you to memorize. The migratory aptitude for this one is one that you would just need to know. Okay? And yes, you will see a test question like this, and it will very likely just be, what is your product? And it's based off the migratory aptitude. Okay? Aldol condensations. You guys remember these, right? Yay! Everybody's excited about it. Okay? We started with an aldehyde in the presence of a base. That base could deprotonate the alpha hydrogen. Why could it deprotonate the alpha hydrogen? If you can remove the hydrogen, it is by definition acidic. Thank you. Now, why is it acidic?
So resonance.
The conjugate base is stable due to resonance. Resonance where it's passing through what special functional group? An enolate. Okay, so we need to remember those pieces. What is special about those? Or let's take a look back at those structures. The two structures for the enolate that are in resonance with each other. Which of those two is the most stable? Top or bottom? Why the bottom more stable than the top? Oxygen can hold the charge better than carbon, which means the bottom one is more stable, which means which one should I actually be looking at? The top, that's the one where my chemistry is. I have a nucleophilic oxygen. That nucleophilic oxygen can react with an electrophile. And if we go through and color, sort of color code, there's my nucleophilic oxygen. One of the assumptions that we make is that we're in a solution with tons of these things floating around. The oxygen can do a nucleophilic addition at the carbonyl. And we would end up with an aldehyde. And what starts to look like an alcohol. How do I make it the alcohol? Add the hydrogen, and I would now have the ald. Oof. Ah! Let's try that again. The ald. Oh, interestingly enough, actually, now that I think about it, we call it an aldol. Which one's higher priority in nomenclature? The aldehyde, and yet the alcohol name is the one at the end. Oh, sorry, just thought of that. The aldol, we typically don't stop at, right? We typically do the last step on elimination. Why do we do that last elimination step? We still have two alpha hydrogens. Why would those alpha hydrogens be susceptible to an acid-base reaction? Why are they acidic? Resonance from the pi bond back with the enolate, and take it a step further, compare them back to our starting aldehyde. Which one's more acidic, blue hydrogens or red hydrogens? Why the blue?
Because there's the two oxygens creating an inductive
Yes.
effect.
What's our rule? Why is that the blue one's more acidic? What rule are we using to call the blue ones more acidic than the red? It's an inductive effect, the effect that everybody wants to jump to first. Now you're right, yes, it's an inductive effect to explain why the blue hydrogens are more acidic than the red. Because of that, we'll get the last step, the elimination. Okay? So, for this to work, I needed alpha hydrogens that were acidic, right? Okay, well, why would we now talk about these? Well, what functional groups have we just now brought in within this new section of material? Don't shout them out all at once. Won't be able to write them down fast enough. What's that? Okay. And aldol was in this, the new functional groups within this unit. Okay, this unit, we had acyl chlorides. Are those alpha hydrogens still acidic?
Yes.
Yep. Okay, I could do aldol, or theoretically do something similar to aldol chemistry here. What other functional groups do I have? I have an ester. Are those hydrogens still acidic? Yes. Okay. Are they as acidic? No. Okay. And in fact, we would typically say they would not react because what resonance? Yes. The oxygen can do resonance N to stabilize that positive charge, making those hydrogens, those red alpha hydrogens, not very acidic at all. Okay? So while I theoretically have them there, I'm losing some of that ability. Okay? Other ones we could do, we could put in an acid, even less acidic. Okay? So if we look at these new functional groups, really the only one that stands out as potential would be the acid chloride or the acid anhydride. The rest of them are actually less acidic than their precursors, and we wouldn't predict a whole lot to come out of it. Okay? So if that was the case, then whoops, no good. If that was the case, then I could go through and add a strong base and a starting ester, and I would expect to see nothing come out of this. Instead, what happens? Something comes out. Because something comes out when I shouldn't have something to come out, stamp, Claisen. Okay, so we get the Claisen condensation. So you've got the idea on what an aldol reaction should be. So you should be able to go through and predict a product for this one. Okay, we've got, if you remember it, the shortcut on how to draw the product of the aldol by drawing out your starting materials, overlaying them, and setting that up. So you should be able to draw me a product. Okay, I want you to take it a step further than a product. I would like to see a mechanism. Okay? And this is one of those ones that I'll give you a hint. Just do it. Okay? As far as I suggested, the alpha hydrogens on the ester are not acidic. Too bad. Do it. Okay? Do it and push through that mechanism and see what you come up with. Okay? I'll give you another couple minute head start. And then, so the first thing we'll show, and then I'll cut back out and draw it out so you guys are back on the mechanism, is remember our shorthand. Draw your carbonyl structure above, draw a second one underneath. Okay? Remember your alpha hydrogens are on the carbon next to the carbonyl. So that's going to be my nucleophile. That is going to attack the carbonyl of the other one. My new bond is now there. Okay, that would be the result of the aldol. Okay, that is unfortunately not the result of the Claisen. Okay, but it at least gets us in the ballpark, and that ballpark is what we want to address. Okay, before we can get the elimination, what would happen? We'd have the negative oxygen, right? What is special about that carbon? 2 words, TI. Thank you, I didn't want to write all those letters out. It's the tetrahedral intermediate. What can happen at the tetrahedral intermediate? The electrons can crash back down and kick out the leaving group. So the result for our final product is actually that guy. You might say, well, doesn't that look ugly? Yes. So if you don't like it, fix it. Okay? If you don't need to make it look pretty, then don't. Okay? So you now know what you're aiming for. So I'm going to get rid of that so we can see that answer. Okay? How many of you actually have the full mechanism already drawn? Okay. So I've already lost that battle. But I'm going to try and draw out the mechanism so we can talk about it. Got up on the board. You should have been able to get to the product in 3 steps. Right? So we have the acidic hydrogen, we remove, we've got our nucleophile. Remember how I said we're drawing the best Lewis structure, but the electrons can come back down, and we still have the active nucleophile. We don't have to show it as the negative carbon. Breaks the pi bond. Okay? We'd have our intermediate. The electrons can come back down, kick out the leaving group, and we'd have our final product. Right? That final product is exactly what's shown as the final product on the slide. But if we attempted to enter that mechanism into, say, smart work, SmartWork has a whole bunch of extra steps, but don't we have the product? Technically, no. If we go back and evaluate, as Farzan had suggested earlier, the ester is not acidic. It isn't. Right? So we would produce very small amounts of the active nucleophile. That nucleophile then could potentially react with another ester, right, to form our tetrahedral intermediate, which is unstable and could equally go backwards as it could go forwards to form our product. Okay? There's nothing to drive towards that ester product. That's not more stable than the starting material. In fact, that product is more unstable than our starting material. Why?
You have acidic hydrogen.
We'll come back to that statement. Why is this product more unstable than our starting material?
Your resonance with that carbon, the carbon in between the oxygens.
There's no resonance there. There wasn't resonance up there either. How many pi bonds in the product? 2. How many pi bonds in the starting material? 1. So 1 pi bond versus 2 pi bonds. 1 pi bond is more stable than 2. We've gone up in energy. Okay? Add to that fact, we started with 2 ester molecules and we now ended with 1. What happened to entropy? It decreased. But that's okay, because entropy always decreases in every system. No, it doesn't. Entropy always increases. Right? So nothing about this reaction is favorable, and yet we're looking at a 68% yield. Okay? So what else happened? Okay? Lisa, what happened? What did SmartWork tell you to do?
To grab the negative oxygen and have it attack the alpha hydrogen.
It said to remove an alpha hydrogen. Right? What structure would that produce? A negative carbon. What did that negative carbon then do?
It took a hydrogen from the H3O plus.
Okay. So there's an interesting observation. H3O plus. What H3O plus?
Second step.
Oh, second step says H3O plus. Notice in our first sequence in black, we didn't talk anything about H3O plus. Okay, so we had no explanation for that. So it can come steal a hydrogen from our H3O plus and it goes back on. So the first step in blue was what kind of a reaction? Acid-base. The second step in blue was acid-base. The first step, what did our species, our desired material act as?
An acid.
An acid. And the second step, what did it act as? A base. So I just drew 2 extra steps that were literally the reverse of each other. That seems kind of stupid, doesn't it? Why would I do that? I didn't. The chemistry did it. Just like those stupid biochemists, the enzyme did it. No, the chemistry actually did it. And we understand why the chemistry did that. What is special about the blue hydrogens in comparison to the red hydrogen I pulled off at the beginning?
They're more acidic.
The blue hydrogens are more acidic than the red hydrogen I started with because I have resonance both directions. Whoops, should not have shown that in red. That is a double resonance stabilized conjugate base. In the starting material, it is a single resonance stabilized intermediate. So the product I've produced has more acidic hydrogens than the beginning, which means I have to do that acid-base step. That is why it's there. I'm forced to do it because the chemistry is there. Why does that help improve our yield? All of the steps up to that black product are reversible and favor the reactant. What happens with that first blue step? That is an irreversible acid-base step. I may get a piss poor yield of the black product that is my final product, okay? But because I'm under basic conditions, that can convert that ester into the enolate form, which is now incredibly stable. The equilibrium is now constantly having product removed. I can constantly convert the black stuff into the blue stuff. Now that I'm done with the reaction, I can finalize the reaction by reversing that acid-base step back to my final product. Okay? Adding the acid isn't going to reverse and cleave that structure apart because there isn't any good system to go through and split that apart with. That's a pretty neat reaction. So Claisen gets to stamp his name to it because he was the first one to discover it and probably the first one to explain why it worked. Yes, the ester we're starting with has a crap acidic hydrogen. It should expect that nothing happens here. And yet it does because of that last acid-base step. It is that acid-base step that drives this reaction. Okay? And that is unfortunately why when you go through and do the homework, as Elisa went through and proved, you have to do a whole bunch of extra mechanistic steps that you're like, why would I do this? I'm already here. Right? The chemistry has to continue through because you have a reactive species. Much the same as if we had a nitrogen in there and we added an acid. Okay? We'd have to over-protonate the nitrogen. Kind of make sense? Okay. So that is our Claisen condensations. They are effectively an aldol reaction in their basic components. We get a slight variation because we can kick out a good leaving group outright without having to do an elimination or doing yeah, let's just leave it at that, even though that statement's wrong. Okay? And we need an acid-base step to finalize it out. Okay? Kind of makes sense? Okay. We just completed the mechanism for that, so we won't worry about completing that as a group, putting it on the boards. So we'll just move on. So there's our full mechanism that goes through and addresses each of those individual pieces. That big step that everybody seems to miss is step 4. Right? And when we look at it on the slides, we're like, we're done before step 4. Okay? Most people don't see that until they have to draw it out. And once they draw it out, they're like, well, now I'm done. I don't understand why I have to go forward. Okay? We have to go forward because it is more acidic, because of that di-ketone functionality. Okay? So, complications for the Claisen reaction. Just like we had for the aldol, we're going to have complications for the Claisen. Take a look at that first reaction. Okay? There's kind of a hint being drawn on that one. It's pointing to a particular position. Okay? If we were to predict this reaction to go forwards, first thing we would do is remove that hydrogen, right? So we'd make our strong nucleophile. We could go through and stack this on top of our carbonyl. Right, we're going to have to rotate that up away from it so we can get in there. Whoops. We'd make our connection. There's our tetrahedral intermediate. We would then kick out our leaving group. We'd have our carbonyl. Everybody kind of see that? So that would be our base structure on what we'd be aiming for. We don't get that as a product. Why not?
We don't have an acidic hydrogen in that, on that carbon. It's on the other side.
Yeah, they are.
That makes sense.
So Sam is saying there's an acidic hydrogen out on the other side of this. Okay, over on the red side, true. Okay. How much of this product do I make? I wish I had that. Oh, I do have. Okay, if we flip back, how much of this product did I make? Shaking your head saying not much. Why? You said it. Okay, we can do a little better than that, hopefully. Was the hydrogen acidic? We're seeing some balking. It's not superacidic. Why is that hydrogen not superacidic in our starting material? What functional group are we looking at? An ester. Why is that red position less acidic? Why is that hydrogen not very acidic? That oxygen does resonance in to stabilize the carbonyl, meaning that carbon or the anion form can't do resonance or does weak resonance. If there's bad resonance, that doesn't mean it can form. I get very little of that hydrogen removed. Which means if I get very little of the hydrogen removed, I have very small amounts of the nucleophile, which means I have very small amounts of the nucleophilic attack, which then means I have very small amounts of the nucleophile elimination to produce the final product. So I would get very small amounts of the final product. Okay? But the reaction occurs. Why does the reaction occur? Is this the final product? No. What happens?
I have an acid base.
I have an acid-base step that removes that hydrogen. It is the removal of that hydrogen that drives this reaction. Now the equilibrium is constantly losing product, so it can constantly reform the intermediate, which is our product, to turn into our final product of the base step. Okay? It is because of that hydrogen that this reaction goes. If that hydrogen isn't there, I don't get the reaction because it can't form enough product. Why is there an issue with this starting material?
That hydrogen isn't there.
There's only one alpha hydrogen. I need two. The first one gets me the nucleophile, but it gets me the nucleophile in piss-poor conditions, okay, or piss-poor amounts. It's the second acidic hydrogen and its removal that actually drives the product formation, not the first. That top reaction fails because I don't have that second hydrogen to remove. Okay? So I get virtually no yield for that top one. The product that I would end up seeing if we wanted to be tricky on an ACS exam which is the starting material. And they would undoubtedly also provide the Claisen product. Okay. Make sense? Okay. So for our Claisens, we have to have that second hydrogen. What happens in the bottom one? Okay. What looks weird or different or interesting about the bottom one, if anything? There's two esters. What does that make that hydrogen in the middle?
Very acidic.
Very acidic. Okay, I get two weak contributions for resonance, but there's two of them as opposed to one. That's effectively saying that hydrogen is roughly the acidity of our ketone or aldehyde. So that hydrogen is pretty solidly acidic. Okay? If it's acidic, what can happen when I place it near ethoxide? An acid-base step. Beautiful. Awesome. I like that idea. Okay? The ethoxide comes in, removes the hydrogen, and we would end up with our active nucleophile. That active nucleophile can do all sorts of fun stuff. Zippity-doo-dah. We all go home, have fun. Yay, there we go. Okay. And I don't know about you guys, but whenever I draw these ones, I see like Homer or something staring at me, like wearing a hat or a moose. He has little eyes, little mouth, antlers. Sorry. But I'm showing two arrows. Two reaction arrows. I didn't change any of the reagents, did I? What else is going on? The hydrogens on the outer ones, as Alexis will tell you, if you go ask her about resonance structures, are not acidic. There is another hydrogen there, but if I removed that hydrogen, it would look the exact same. So why bother?
They act as a nucleophile?
Ethoxide is a negatively charged structure, relatively small. It can act as both a base or a nucleophile. If it acts as a nucleophile, what happens? Where's the electrophilic carbon? Our carbonyl. We would break the pi bond, and then what happens? What's that? Then what happens? You reform your pi bond. This is your standard nucleophile addition and elimination. Is anybody seeing any issues yet?
It still has the same reactivity.
Yes, it does have the same reactivity. I still have alpha hydrogens that I could have be nucleophilic, yes. So let's say I go through and do that. Say I remove those hydrogens. Compare those nucleophiles for me.
They're the same.
What does ET stand for? Ethyl. What does ethyl mean?
Two carbons.
Are they the same?
No, but the
No.
strength of the nucleophile.
So the strength of the nucleophile is the same, but I have two different nucleophiles, which means how many products do I get? Two different products. Okay. Add that fact that there's a second electrophilic site. The ethoxide could also attack there. How many products do I get? 3 products. Okay. Is that a good reaction to run? No. So our first complication, we have to have 2 alpha hydrogens. The second complication, the base we choose to initiate this reaction has to be very carefully selected. That base needs to match the leaving group. This is ethoxide. What's our leaving group? Methoxide. Okay, so if we go through and look at each of these cases, look at the one above. Okay, it's ethoxide, 2 carbons and an oxygen. What's in the starting material? It's an ethyl ester. If we go back to the previous questions on the other side, okay, what did we start with? Ethoxide, 2 carbons and our oxygen. What was our leaving group? 2 carbons and an oxygen. We have to make sure that our leaving group is the same as our nucleophile. If it is different, then we end up with different possible products coming out at the end, and that can mess with our product isolation. So we need to be careful when we go through and design those. Kind of make sense? Okay. Where we will start on Wednesday is looking at our crossed reactions. Remember with the aldol, when we had different starting aldehydes and ketones, we had to be very careful with what we used because that could generate multiple products, multiple nucleophiles, multiple electrophiles. The same issue pops up with our Claisen reactions.